What is the state of motion? How do you define the state of motion? You see, state of motion is the status of the particle's motion parameters with respect to time. What are the key parameters? Position, velocity, acceleration, in fact, even shape and size and direction. I'll repeat, position, velocity, acceleration, shape and size, direction. All these key parameters monitored with time completely will tell you the status or the state of motion. For example, rest is a state of motion. Moving with constant speed in one direction, same direction, that is uniform velocity, is a state of motion. Moving with constant speed but changing directions, that is the changing velocity or under acceleration part, is a state of motion. Or moving with non-uniform velocity, accelerating, changing speed and changing direction could also be a state of motion. So, as I said, position, velocity, acceleration, shape and size and direction, all these parameters, the whole story with time gives you state of motion. And what does the force do or attempts to do? Force attempts or tends to change the state of motion. Mind you, it may not be successful in doing that, but the tendency is to do that. Understood? So a force is a push or a pull that tends to change the state of motion of the body. All right. If I quantify what a force can do in layman language, okay, daily language, what can a force do? Move a body, stop a body, break a body. It can break it, shake it, and make it. All right. That's what force can do. But this is layman's language. All right. There's nothing wrong with that. But what if I want to formalize this discussion? So move a body, stop a body, break a body could mean force can change direction of a body, force can change speed of the body, or force can change the shape of the body. Well, I am not saying that the force is compelled to do only one of these. It's not an exam which force is giving, and it's not an MCQ that force has to pick a correct option. No, more than one can be correct. Force can change the speed and the direction. Force can change the shape and the direction. Well, a typical accident. The car gets jammed, right? It gets totaled and the direction is changed. Speed is changed. All three is possible. But the tendency is to change. Tendency is to change the state of motion. All right? Okay. It's a vector quantity. Well, sir, vector quantity. Yes, sir, we recall vectors are those physical quantities which have magnitude and direction. Wrong. A vector does not have only two checkpoints. In fact, come on. Force versus electric current was the very concept which introduced us to not two, but three-pronged criteria to call a quantity vector. Magnitude, check. Direction, check. There was one more guy. They have their own laws of vector algebra because 10 plus 10 could be 0, 10 plus 10 could be 10, 10 plus 10 could be 20. Unlike real numbers, vectors don't add like 1 plus 1 equal to 2. They have their own algebra, they have their own addition, they have their own multiplication. Those quantities are called vector, and guess what? Force is a vector quantity. 300 years on and till today, we are at a checkpoint in unifying all the forces of nature. Let me give you an example first of all, what I want to tell you. So you see, in 19th century, 18th, close to the end of 18th century and the beginning of 19th century, whenever a new interaction was discovered, they used to call that interaction's name by what it was doing. Okay, for example, let's say, assume it, be with me. Let's say sun and moon are interacting with each other. Let's say moon and earth are interacting with each other. Initially, it was called the sun-earth interaction and moon-earth interaction. It was thought that the sun and the earth interaction is different. The moon and the earth interaction is different. But later it was established that they both are nothing but the force of gravitation. You see, different interactions, but the nature could be same. So initially, there were hundreds of kinds of forces known to us. Why? Because every time somebody discovered a force, they used to name that force either after themselves or after what they're observing. So there was a planetary force, there was a cosmic force, there could be an asteroid force, right? There could be a microscopic force, electron-proton force, pi-meson force, boson force, whatnot. You discover something, you discover a force, you name it. But later on, it was discovered that all the forces in the universe, can be put into one of the four fundamental forces in nature. That means whatever forces we knew belong to one of the four baskets. They all belong to one of the four baskets. And the hope is that as after some time, even these four baskets may club and become one basket. And that's what we call as unified theory of science. All fundamental forces and the relationship between elementary particles in terms of a single theoretical framework. I will not take a detour here, but if you have heard of something called the string theory is the closest and so far the best attempt in unifying the theory of science. It's not completely successful yet. What I mean to say is that two charges interact, electric force. Two masses interact, gravitation force. Can I explain the two charge interaction and the two mass interaction by the same property? Well, till now, the clarity is not complete. But the pursuit has a name, and the name is unified theory of science. All right? Till today, there are four fundamental forces in nature. Okay? Let's talk about all four. Till today, there are four fundamental forces in nature, namely gravitational, strong nuclear, electromagnetic, and weak nuclear. Of course, over our course of 2-year preparation, we will encounter each of them in great detail. But right now, let me just give you a small preview of what each represents. First is, of course, the gravitational force. Any two bodies attract each other by virtue of their masses. If body has a mass, it will attract another body having mass. Gravitational force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. First of all, two things important about gravitational force: whether it's an electron proton, the mass is in the order of 10 to the power minus 30 kgs, or it's planets. Each mass attracts another mass with a force called gravitation. The force is always attractive in nature, and that force is proportional to m1 m2 upon r square, directly proportional to the product of the masses and inversely proportional to the square of the separation between them. All right? Then comes the strong nuclear force. The word itself has strong in it because it is the strongest interaction. It is the interaction which acts between the nucleons. What are the nucleons? The particles inside the nucleus, that is protons and neutrons. Okay, this is also called the effective nuclear charge sometimes, rightly or wrongly, but it actually means that strong nuclear bonding between the protons and the neutrons. It is the strongest of all the fundamental forces. Okay, then comes the weak nuclear. The name itself suggests it's the weak force. All right, this is the force which is responsible for the neutron to change itself into a proton. Spoiler alert, we will study later, but if you ever come across a word called beta plus decay or beta minus decay, I'm not trying to show off or intimidate you right now. Forget about it. But if you see that word, beta decay, could be a beta plus decay, could be a beta minus decay, the force which is involved in such interaction is actually the weak nuclear force. It is the force responsible for the neutron to change itself into a proton and vice versa. Of course, the reason being to attain the state of stability. Considerably short range force with a range much smaller than even the size of proton or neutron. Can you imagine how weak this force is? Well, there is a reason why we call it the weak force. Okay. Next comes the electromagnetic force. Electromagnetic force. It is actually a culmination of two kinds of forces, which we will see later. There is a reason why we combined them. Okay. One is electrostatic, and of course, one is electrodynamic. Static means if two electric charges are at rest, they exert a force on each other. That's electrostatic. And if the charged particles move, then also they generate a force, which is electrodynamic. Right now, I don't want to get into the math of it, but understand something. 4 kinds of forces, namely gravitational, strong nuclear, weak nuclear, and electromagnetic. Every force in the universe belongs to either one of these 4 sets. And at this junction, I am going to introduce some standard forces which we have to deal with for the next 2 years. Arch your back, take a deep breath, let's go. Notebooks ready, pen ready. All right? Okay. First is contact force. This is extremely, extremely important. When 2 bodies are in contact, any 2 bodies, contact means literally physical contact. They experience a force. Why, sir? See, when 2 bodies are in contact with each other, you see what happens is the particles of 1 and the particles of 2, they will interact with each other. Correct? Using charges. Because the range is high, the force which is of most relevance here is electromagnetic force. So first of all, what I'm about to study, the contact force, belongs to which bucket? Sir, electromagnetic bucket. Correct. Point number 1. Point number 2, the reason. The reason is electrons and protons of the 2 bodies in contact will experience each other. How many forces do you think will be because of these interactions? Sir, millions and billions and trillions and zillions and googlions of the forces. Correct. But if I add all those forces vectorially, the resultant of all those interactions between the electron-proton of body 1 and electron-proton of body 2, which are in contact, is called contact force. Where do you think the contact force will act? Sir, any random direction. Agreed. This contact force, R, acts in a random direction. Random direction. Why? Because there is no logic to where it will go. But if I divide this force into 2 components, one component will come parallel to the contact surface. This is called the contact surface, or from now on, I will use the word interface. Contact surface or interface. Okay? One of the force, one component, I'm calling it R parallel, will come parallel to the interface. One component, I'm calling it R perpendicular, will come perpendicular to the interface. The component which is parallel is and will be known as friction force. This small boy grows up to become friction one day. Why? Because till I mention otherwise, everything is frictionless, everything is smooth. There is no friction anywhere till I say so. Understood? Okay. The perpendicular component of contact force is called normal force, or the more popular name is normal reaction. Understood? So if somebody mentions contact force, ring a bell. Contact force has 2 components. One is parallel, one is perpendicular. Parallel one is called friction. Perpendicular one is called normal reaction. Okay? And second point is, until I say so, there is no friction. Understood? So 2 components are parallel to the surface, perpendicular to the surface. Since friction is out of the window for the time being, what matters is the normal force or normal reaction. Can you see? This block is kind of on the table. Okay? So there is a normal force which is being exerted on this block. What are the properties of this normal reaction? First of all, the word is normal reaction. Let's go back. What is the direction of the force on this thing? Normal, because this angle is 90. Hence the word normal. That's the first important point. Second is, it is perpendicular to the interface between. Correct? But sir, what if it's not a straight line? What if it's angle, wedge or something? There you go. Can you see? It's a wedge, inclined plane. But where is the interface? This is the interface. Where do you think that normal will be right now? Which direction? Up, right, left, down? Which normal? it would be normal reaction in this way. This will be the normal reaction. Did you understand that? In this case, this will be the normal reaction. Also, so two important properties about normal reaction which we just learned. First is, it's always normal. Normal to what? Normal to the surface, contact surface, or normal to the interface. And what is the another quantity? Another important property about normal reaction is, normal reaction is always pushing in nature. What does it mean? It means that where is this block kept on the table pushing the table? Down. Where is the table pushing the block? Away. Normal reaction can't pull, it can only push. Where is this block pushing the wedge? Down. Where is this wedge pushing the block? Away. So, two things about normal reaction. A, it is always perpendicular or normal to the surface in contact. Fancy name for that? Interface. Point number two, normal reaction is always pushing in nature. That is standard force number one, called contact force. Standard force number two, weight. The most misunderstood force. What is weight? Sir, weight is something which we all want to lose. Agreed. I'm working on it actually. Weight is something which we all want to lose. That's fine. That's good wishful thinking. But what is actually weight? Weight is the force experienced by a body due to gravity near the Earth's surface. First of all, gravity is not a personal property of Earth. You have to understand something. Gravity is not a personal property of Earth. The force between Moon and the Earth is gravitational force. The force between Sun and the Earth is gravitational force. The force between 1 microgram of a grain of sand and the Earth is gravitational force. Please don't confuse the word weight with gravitational force. No. So that one is clear. Gravitational force is the force of attraction between any two masses. However, when we specifically talk about Earth, point number one, and specifically talk about near the Earth's surface. What's so special about near the Earth's surface? You see, near the Earth's surface, F is equal to, you will study later, it is G m1 m2 by r square. Everybody has read this at one point of the time in their textbooks in 9th or 10th standard, I'm sure. Even if you have not, it's okay. But when one of the mass becomes the Earth, Gm Earth, and the other mass is any mass which is very, very close to Earth, then the distance between them is approximately equal to the radius of the Earth itself. And then everything else becomes a constant. And that is the reason why the weight is the force of an object of mass m towards the Earth, near the surface of the Earth, is mg. So what is this mg coming out to be? This mg is nothing but g, mass of the Earth, radius of the Earth square into the mass of the body. This guy is g. And that's why we call it weight. So weight, don't confuse the word weight or gravity with gravitational force. No. Gravitational force is between any two masses, interplanetary or microscopic. But gravity word and the weight word we usually reserve for Earth. Okay? So what is the weight? Weight is equal to mg, where g of course is acceleration due to gravity, which we all call as 9.8 meter per second square. Also, as the body goes away from the Earth, the value of g changes. So this 9.8 meter per second square is valid only for what? Near the surface of the Earth. Alright guys, so weight is the force with which Earth pulls. Now, one more thing. Understand the difference between Earth and ground. For example, if this is the Earth and I ask you, where is the weight acting of this block? Sir, towards center. Absolutely correct, my friend. If I ask you, this block, where is the weight acting? Towards center, sir. Absolutely correct, my friend. And if the block is here, where is the weight acting? Sir, towards the center. Agreed. But in our lab, you and me are in lab right now. When we analyze, we draw the ground flat. And the block is kept on the ground like this. If I ask you now, where is the weight acting? Weight will act vertically down, mg. Did you get it? Earth is round. Ground is flat. Please don't mistake it. But sir, how can ground be flat? Because ground is that part of the earth which I have zoomed in to just look at the mass. This very small patch. So earth is round, nobody is disputing that. But the ground is drawn as flat. Drawn as flat. Okay? And vertically down is the weight. And of course, where will the normal reaction be in this case? Normal, up. Got it? Perfect. Next standard force. Contact force, check. Two components of contact force, normal and friction, check. Second, weight, check. Third is tension. Very, very popular, very, very common. Extremely simple to understand. Well, this guy in the cowboy hat and the long boots is pulling a string. The string in his hands right now is slack. What is the word? Slack. Slack means unextended, loose. When he pulls it, the string is taut. So what are the two words which I just taught you? What I taught you is T-A-U-G-H-T. I taught you taut, T-A-U-T. What does slack mean? Slack means loose and taut means extended or tend to extend. You see, when a string is attempted by pulling at both ends, it's attempted to change its length. The string resists. And the string resists by being in the state of resistance. This state of resistance is called tension. So what is the tension? Tension is the tendency or the measure of the tendency of a string to resist any kind of change or any attempt to change in its original composition. If the string is tied here, and this is how the cowboy is pulling it, isn't the cowboy trying to change? The wall and the cowboy both are pulling it apart. So what will the string do? No, you can't pull me apart. So the string will exert a tensile force or tension on the wall towards the right side, on the cowboy towards the left side. You know why? Because string, unlike normal reaction, is always pulling in nature. And it acts always away from the tied ends. Where is the tied end of the string? On the wall, out here. Away from it, towards right. Where is the another tied end? In the hands of the cowboy. Away from it, to the left side. Alright? So, summary. Any string, when it's trying to be stretched, does not want to get stretched. What does it do? It retaliates. What is the measure of that resistance or retaliation? Tensile force. Got it? In short, tension. Where does it act? It always acts away from the tied ends. Where whoever is pulling it, tension will be away from it. Opposite to that direction. Second point, it is always pulling in nature. Did you get that up till now? Alright. One more question, sir. Sir, why is this T force which you have just drawn same here and here? Is the floor which we are working on frictionless? Yes, sir. Similarly, there is something called an ideal string, which we will study in today's or the next session. What is ideal string? Ideal string is something called a massless string. Sir, how can the mass be zero of a string? I know it. How can the friction be zero? But we do something called idealize the system. So, till I mention it again, a string will be considered to be ideal. And ideal string means massless string. And if the string is massless, the tension force throughout the string remains same. Three things you learned here. First, tension always pulls. 2, tension is always away from the tied ends. 3, if the string is massless, tension throughout the string remains same. 3 standard forces now. Contact check, weight check, tension check. Normal, always pushing. Tension, always pulling. Weight, always near the surface of the earth. Got it? We are ready for now to jump into the world of Newton's laws of motion. 3 physical laws. that together laid the foundation for classical mechanics. And in Mr. Newton's honor, this is also called Newtonian mechanics. And in Mr. Galileo's honor, it is also called Galilean mechanics. It was started by Mr. Galileo Galilei. What a name. It was started by Mr. Galileo Galilei, Italian, okay? But Mr. Newton carried it forward and took it to the next level. It describes a relationship between a body and the forces acting upon it and its motion in response to these forces. There is something called stimulus. There is something called stimulus and there is something called response. And stimulus brings response. Who is stimulus? Force. And what is the response of the force? That is what we are trying to understand. And who helps us? Mr. Newton and his 3 laws. Understood? That is the agenda. You see, first law will deal with qualitative aspect of the force. What is qualitative? When we don't talk numbers, we talk theory. Second law will offer the quantitative when we will talk numbers. And third will actually teach us something really, really brilliant. And that is that a single force doesn't exist. In nature, the force exists in pairs. I'll repeat. What is the first law giving you? Qualitative aspect of force on the system. Effect of force. Qualitative effect of the force on the system. Second, what does second law gives you? Quantitative aspect of the force with the system. And the third one will establish that a single force can't exist. You know what? When I was a student, I was most intrigued by the third law. Single force can't exist. So let's unravel the mystery and let's dive into the world of Newton's laws. Ready? Arch your back. Deep breath. Let's go. First, Newton's first law of motion. Every object will remain. Guys, understand the official definition. Understand the explanation. It's not that one is more important than the other. Pay attention to all of this. I know today we are understanding most of the theory part. I know theory part is less engaging on the surface as compared to numericals, because numericals give you a kinetic feeling of it. Now, everybody wants to be kinetic because static is associated with laziness or lethargy. But believe me, unless theory is clear, you will be running without the purpose. So if you want your kinetics to make sense, pay attention and don't ignore the statics. Understood? So come on, ready? Newton's first law of motion. Every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. In other words, nothing's gonna change until someone tries to change it. This statement is deep. There is a philosophical tangent to it. Nothing changes in the world, in the universe, things around you, things inside you, or in your life. Nothing will change unless an attempt is made to change it. Okay? Praying that it change, hoping that it change may give you relief. It will not change things. Even the prayers work when they are backed by action. You see, I talk a lot, but when there is an opportunity to give you some knowledge, and from my experience, I don't lose a chance. Circle back. A system. This block is a system. There are multiple forces acting on it. In this case, I have taken 3, F1, F2, F3. First of all, add all 3 forces. Add all 3 forces. Okay? If addition of all 3 forces is 0, then the acceleration is 0. What you have on this slide are 2 ways to understand first law. Okay? Way number 1. Nothing changes if no attempt is made. That means if body is at rest, it will continue to be at rest. If body is moving, it will continue to move with the same velocity, same direction until a force acts on it. Sir, if a force acts on it, it's guaranteed it will move? No. Net force. Look at this thing. 3 forces. F1, F2, F3. Is F1 0? No. Is F2 0? No. Is F3 0? No. But what if Adding all three of them gives me 0. Then what will the system experience? I don't care. In other words, if this block is at rest and this block is being pushed from both the sides by the same force of 10 Newton, then both the block will still remain at rest. If it was initially at rest, the 10 Newton and 10 Newton gets cancelled. So it's not about a force. It's not about multiple forces. It's about what? It's about a non-zero net force. So a body will exhibit any change if a non-zero external force is applied on it. The name for this particular law, every object will remain at rest, as they said, if the vector sum of all the forces acting on a particle is 0, then the particle remains unaccelerated. You see, I have the answer to the question. Stimulus gives response. Remember? And I said stimulus is force. I can call the stimulus as the cause. And what is the response? The response is acceleration. If there is stimulus, there will be response. If there is a cause, there will be effect. If there is a force, there will be an acceleration. And if there is no force, there is no acceleration. If there is no acceleration, there is no change in speed, there is no change in direction, there is no change in state of motion. That's the first law of motion, and it is also called the law of inertia. Because a body's tendency to hold on to what it was doing before is called inertia. Inertia of rest. That means if a body is at rest, it continues to be at rest if you don't try to change it. If the body is in motion, it continues to move in the same direction with the same speed if no change is made. And inertia of direction, that means if it's in the same direction, it will keep on moving unless you try to change it. Inertia is the resistance of a particle to change its state of rest or of uniform motion along a straight line. In other words, inertia is meaning or standing for resistance to change. That's why inert gases, inert. Remember, inertia is resistance to change. Got it? Perfect. Second law of motion. First one was qualitative. Second one is quantitative. Don't worry, I'm listing the laws right now. So understand the basic concept of every law. Okay? Be with me, guys. Come on, it's important. Second law gives you quantitative. Who was the cause? Force was the cause. Who was the effect? Acceleration was the effect. First law said, if there is a force, there will be acceleration. Second law says that, and that acceleration will be equal to the net force which you applied upon mass. Acceleration of a particle measured from an inertial frame. Ignore this word for right now. For right now, inertial frame for us is ground. Right now, inertial frame is ground. So I'll say this again. The acceleration of a particle as measured from ground is given by the vector sum of all the forces divided by what? Mass. A equal to F by M, or more popularly what you call is F equal to ma. Remember, I will deal with each law in detail, especially the second one. But right now, the statement is fine. First law tells you cause brings effect. Second law tells you the mathematics between effect and cause. A equal to F by M. Like for example, where is it coming from? Where is it coming from? First law is called law of inertia. Look at it again. A equal to F by M. First law was called law of inertia. Where is this coming from? This is actually coming from the name itself. Second law of motion is called law of momentum. Have you heard this word before? Momentum P is equal to mv. M is the mass, v is the velocity. Since velocity is a vector, momentum is also a vector. So the second law, the more popular version of second law, which all of you studied in lower standard, was F equal to ma. But where is it coming from? It's coming from the statement, the rate of change of momentum is directly proportional to the net external force acting on the net external force and in the direction of the net force. What does it mean? It means Force was the cause. What does the force bring about actually? So, I said acceleration before, but there is deeper concept attached to it. Force brings about change in momentum. But sir, you said acceleration. Now I'm confused, sir. Oh, confused? Hold on. Arch your back. Let me clear the board. Let's go. Second law says that force is proportional to dP by dt. What is P? P is the momentum. Okay. What is P? mv. Okay. So when a proportionality becomes a equality, you add a constant. Let the constant be K. If the mass is constant, can I take mass out of the differentiation? Because it's just multiplying the differentiation? Yes, sir, you can. So F is equal to m dv by dt with K being taken as 1. All right, sir. And what is dv by dt? Oh, dv by dt is A. That's how it's coming from. Did you understand? F equal to ma is a special case of Newton's second law if mass is constant. But sir, mass is always constant. You think? Is your mass constant? While I am talking, is my mass constant? Yeah, of course, sir. No, it's not. I'm talking. Isn't my energy being spent? So mass is not constant. A car is being driven constantly. Fuel is getting burnt up. In fact, in the universe, mass is actually more situations not constant than constant. So don't take it like duh. No, it's not duh. Okay, so remember, F equal to ma is actually valid if the mass is constant. But unless I mention otherwise, the mass is constant. Newton's second law, law of momentum. What does it tell you? Net force is equal to the rate of change in momentum. And if mass is constant, it becomes F equal to ma. First law, law of inertia. Second law, law of momentum. First tells me cause brings effect. Up till now, I was thinking effect is only acceleration. It's much more than that. Effect is change in momentum with time, which culminates into acceleration. All right. Simple application. You have a 5 kg mass, constant. A 3 Newton force is being exerted on a smooth floor. How many forces do you think are acting on this 5 kg block? Sir, 3 Newton. No. There is a weight acting, mg, which in this case is 5 times 10. There is a normal reaction by the ground below, the floor below on the block. So what about the friction? The word is smooth, sir. But in my experience, this will go in the right direction with an acceleration A. And since F equal to ma, F is 3 Newton in this case. So acceleration will also be along the 3 Newton force, which will be equal to 5 times A. A is 3 by 5 meter per second square, the SI unit. Did you get it? 3 by 5 is 0.6. Simple application. All right. Okay. The most intriguing, the most detailed, here comes the Newton's third law of motion. If a body A, what was the claim I set on Newton's third law? The claim was a single force does not exist. Nature, force exists in pairs. This is an unbelievably powerful statement. Unbelievably powerful statement. A single force does not exist. Interaction. The word interaction means interaction. Inter happens between two bodies. Okay, let me elaborate for you. If a body A exerts a force F on another body B, any body A exerts a force on another body B, then B exerts a force minus F on A, and the two forces acting along the line joining the bodies. Brilliant. Brilliant. Let's say A exerts a force on B. We call it FBA. Let me explain to you the subscript meaning. There are two letters in the subscript B and A. The first letter B describes on, and the second letter is by. So what is this? This is force on B by A. FBA, force on B. The first letter of the subscript is the recipient, on. The second letter of the subscript is the source, who. Okay. So FBA is force on B by A. All right, erase it. So A exerts a force on B. Check. B exerts a force on A. Check. What the third law is saying? The third law is saying that, first of all, these two forces are equal in magnitude. Okay. And second, they are acting along the same line but opposite direction. Wow. Okay. Sir, is this always true? Yes, sir, it's always true. But sir, weight. What about weight? Where is the other body of the weight? The other body of the weight is Earth. Earth pulls you down with mg. Okay. So sir, we pull the Earth back. Of course, yes. You pull the Earth back with the same force mg. All right. Sir, there are two blocks A and B. Yes, sir. There is a force by A on B and B on A. Yes. No force exists solo. Every force exists in pair. Let me elaborate this whole thing with the help of some examples. Okay, watch. Tanker, big tank, tons and tons of weight. All right, takes aim. Boom. Action, reaction. Let me introduce you the more famous name of the Newton's third law. Action, reaction law. Does it ring a bell? Oh, yes, sir, yes, sir, yes, sir, it does ring a bell. For every action, there is an equal and opposite reaction. But sir, why didn't you tell so at the beginning? Why didn't you tell this definition to us before? This is so nice. We know this. To every action, there is an equal and opposite reaction. There is a reason why I did not give you this definition before. Because this definition is not wrong, but it is misleading. I'll tell you why it's misleading. Are you ready? Let's look at this beautiful tank again, one more time. Action-reaction pair. The two forces in the Newton's third law are called the action-reaction pair. The tank takes aim. Boom! The boom is action, the cannon going forward, and the tank getting jittery, or recoil of the tank is the reaction. Agreed? All of you understood this. All right. And my claim is that it is not completely correct. There is something missing. Do you want to know what's missing? Shall we understand more examples first and then see what is the missing part? All right, let's go. How does a rocket get launched into space? The fuel inside the rocket is burnt and then thrown out at such a fast rate that the rocket itself gets pushed upwards. Really? That's how the plane flies. That's how the rocket gets launched. It's through the law of action-reaction. Again, I'm using the word law of action-reaction in place of Newton's third law of motion only because it resonates with you. I will dispel the myth around action-reaction law that yes, it is not completely correct. Hold on. But let's first tabulate the examples of action-reaction. First, I gave you the tank or the gun. When you shoot a gun, there is a recoil on the shoulder. Why? The gun exerts a force on the bullet exerts a force back on the gun. Rocket throws the fuel down. So rocket pushes the fuel down, burnt fuel down, fumes, and the fumes push the rocket up. Law of action-reaction. Newton's third law of motion. Swimmer. I can cycle at one place when inside the ocean or a pool. But if I want to swim ahead, what do? I actually cut the water with my hand and then push it backwards. So the water gets pushed backward and I get pushed forward. So the swimmer exerts the force on the water backward. The water exerts the force on the swimmer forward. Action, reaction. Newton's third law of motion. Time to tabulate the property of action reaction and then I will tell you what's wrong. Okay. What's wrong is the word reaction. Reaction. Reaction means response to action. It means action comes first and then the response comes. There is a problem. I read one beautiful sociological explanation of the Newton's third law. It was beautiful. Who comes first? A child or a mother? I'm not asking about the woman who's giving birth to the child. I'm asking who comes first. Is the child coming into the world first, or the woman who's delivering the child becomes a mother first? Both. Because as soon as the child is here, the mother is here too. Beautiful, isn't it? It's not that the child comes first and then the woman becomes mother. No. This beautiful bond between a mother and a child is simultaneous, isn't it? So beautiful. So my problem is with the word reaction. Okay, I'll give you one more example. There is a boat. You're standing on the boat. The boat is near the shore and you are about to jump forward to come on the shore. What do? In your experience, anybody who has done this before, what's your experience? So experience is very simple. You should jump more than you think is required. Come on, you have to agree with me. If you are on the boat and this is, let's say, this is water and the boat has reached the shore. This is the shore. And this is the boat. And you are here. If you want to land safely on the shore, what do? You take a jump and land. But in your experience, you know that the moment you jump, the boat will go back. So in your experience, you take a bigger leap than expected. Now tell me, when do you think the boat goes back? After your jump? No. You know when the boat goes back? The moment you think about jumping. Because when you think about jumping, you bend your knees, you take a stance forward, your hand is like this and that's the jump. So the moment that comes from your grunt, the moment you involve your core, you push the boat and the boat pushes you. Action, reaction. No. Action, action. This law should be called action 1, action 2, not action, reaction. I'm okay with the name till you don't get confused that it's not the reaction. It's not that you fire the bullet. The bullet says, okay, bye, I'm leaving. And the boat thinks, oh, the bullet is leaving, let's get recoiled. No, it's not like that. The bullet gets fired, immediately the gun gets recoiled at the same time. So here are the properties. And let me explain the properties in the real time. Can you see this beer kept on the cube? Can you see the normal reaction? Up till now it was ground for you. Deliberately it's block on block now. A sphere on block. Can you see N? The normal reaction exerted by body 1 on body 2. Can you see this N again on body 1 by body 2? So there is a N12, there is a N21 situation. Correct? It's simultaneous. Look again. Look again. The block, simultaneous. I can call it action reaction, but I will never do the mistake that they are one follows the other. No, sir, it does not. In fact, it occurs simultaneously. Watch. Guys, pay attention on what's appearing on the text and pay attention to the changes it making the diagram. I'll repeat. Pay attention on what the property is appearing and keep a lookout on the diagram. First, simultaneous. Watch. Both the arrows came simultaneous. Opposite direction. So the first property is occur simultaneously. So reaction is not the response to action. It's action 1, action 2 at the same time. Second property, opposite direction. One more time. Can you see the arrows pointing in opposite directions? Good. Third, act along the same line. Can you see the support? The support of the two vectors is same. Can you see the dotted line? That's the support. In this case, one is upwards, one is downwards along the same line. Different objects. Different objects. This guy, upward force is acting on the sphere. Downward force is acting on the block. Different objects. Because there are two bodies involved. Equal magnitude and equal nature and same nature. What does it mean? It's the same kind of force. The upper N is also normal reaction. The lower N is also normal reaction. And equal magnitude, let's use a ruler. Can you see a ruler? If this ruler measures the length between the two red lines of the upper vector, the same ruler will say that the blue line is also between the two reds. Property number 1, occurs simultaneously. Property number 2, opposite direction. Property number 3, act along the same line. Property number 4, different objects. Property number 5, equal magnitude, same nature. 30 seconds. Take a look again. Take your time. Take your time. Newton's third law, law of action reaction. I am okay with the name action reaction as long as you don't think that reaction follows action. No, sir, no. It's simultaneous. Got the properties? Keep these 5 properties of Newton's third law in mind. Shall I go ahead? All right. So I have dispelled the myth. What was the myth, sir? The myth was that reaction follows action. The myth was this. Response to action is the meaning of the word reaction. These are the 5 properties. Occur simultaneously. Response to action is wrong. It is simultaneous. Did you understand this part or not? Did you understand Newton's third law or not? Did you understand Newton's first, second, and third law or not? Okay. So what did we do today? I introduced the unified theory of science and saying that every force in this universe belongs to one of the 4 sets, namely gravitational, electromagnetic, strong nuclear, weak nuclear. Agreed? Then I introduced some standard forces to you. Contact force, 2 components, normal and friction. Then came weight. Then came tension force. Then came the 3 laws of motion. Agenda is very simple. First law, qualitative. Second law, quantitative. And third tells you that a single force does not exist. These laws, if you notice, the first and the third are more theoretical and qualitative in nature, equally important. The second one is more about the math part. The first law is called law of inertia. Without any external force, nothing will change. Second law is called law of momentum. That means F equals change in momentum upon time taken, which if mass is constant becomes F equal to ma. Third says that solo force cannot exist. They occur in pairs. And the 5 properties are as follows. This was the introduction to Newton's laws of motion. Never ignore the theory. Otherwise, the numericals will ignore you. So please make sure you have understood everything. In the next session, I will introduce you to the more quantitative aspect of this. Till we meet again, this is Apurv Mathur signing off, and we are Byju's the Learning app. Stay home, stay safe, and keep learning. Have a great